let's hop right into chemical reactions then. So chapter 7, finally talking about chemical reactions. So this is where knowing those polyatomic ions is going to help a ton, because if you can look at the polyatomic ion, recognize it. So vinegar there actually is one of the polyatomic ions that's on the list. It's also known as acetic acid. Being able to recognize those at a glance instead of having to go and try and match them up on a list to figure them out, it's going to save you a lot of brain power, and it's going to save you a lot of time. So chemical reactions, we talked about chemical reactions. There were a couple questions on the, or chemical changes, or also chemical reactions. A couple questions like that on the exam. The chemical reactions involve the transformation of one or more substances into different substances. So the classic model volcano you make with baking soda, which is sodium hydrogen carbonate or bicarbonate, reacts with acetic acid or vinegar to form CO2, gas, water, and sodium acetate. You get carbon dioxide bubbling out of the mixture, and that's what causes the eruption. Usually put a little dish soap in there, which doesn't participate in the reaction, but gives you lots of bubbles. So reactions that occur in liquids and form gases are gas evolution reactions. We're going to go over a whole bunch of types of reactions. Just double check something real quick. All right, cool. So automobiles driven by reactions. We have hydrocarbons such as octane, which comes from, or is part of gasoline. It combines with oxygen in the air, reacts to form carbon dioxide and water. That carbon dioxide is really hot, and that hot gas expands, which is what pushes the pistons to make your car go. Combustion reactions are another subcategory of oxidation reduction reactions in which electrons are transferred from one substance to another. So this is where, actually, after this chapter, we'll do just a little bit of chapter 16 before going back to chapter 8. So we're taking these molecules, ripping them apart, and then putting them back together in a new way, and out of that we get energy. Laundry detergent works better than hand soap for washing clothes because it contains substances that soften hard water, which is a big thing around here. That's why you get like hard water deposits on things. It's these different minerals dropping out of solution, becoming solids. So hard water contains dissolved calcium and magnesium ions, which interfere with the action of soap by reacting with it to form a gray, slimy, sludgy, disgusting scum. I think it's in the next, yeah. But in laundry detergents, they contain substances like sodium carbonate, which, when you add it to water, breaks apart into sodium ions and to carbonate ions, another polyatomic ion, one of the ones that's on the list. This then reacts with your calcium magnesium ions and prevents them from interfering with the soap. So you can have these solids settle to the bottom of the laundry mixture, and you don't get that gray scuzz. So this is an example of a precipitation reaction where you have two liquids that mix together and you get a solid out of them, or solid that forms. So if we could look at, on the teeny tiny scale of atoms and molecules, it would be really easy to tell if we had a chemical change or a chemical reaction, because you would see the individual molecules splitting apart and then reforming into new molecules. Of course, that's impossible. So we have other ways of identifying chemical reactions. One of the big ones is a color change. Some chemical reactions are reversible. This is an example of one. So you have these molecules that are embedded in the plastic of a spoon, and it changes color because the molecules, as they heat up, change shape. And that changes the way that they interact with light.
May I have your attention, please? This is Aqueous IED.
So one of the other ways that we tell if we have a chemical reaction happening is we get the formation of a solid. So if you pour, in this case we have this yellow liquid being poured into the red liquid, or sorry, clear liquid, and this red cloudiness is a solid that's being precipitated out of solution. That's also why, related that rain is called precipitation, because it's two gases mixing together and forming a liquid out of the air. So a precipitation reaction or formation of a solid is evidence of a reaction. One of the other ones is the formation of a gas. If you remember, a couple weeks ago we did the lab where we had, to identify these as physical or chemical changes. The most important thing when identifying a gas in a solution is that there's a continuous formation of gas bubbles. Because you can drop something into water and you'll get some bubbles. And in fact, even sometimes, depending on where your water comes from, out of the tap, it'll look like it's forming bubbles. But that's just because there's a lot of air in your water. So dropping an Alka-Seltzer tablet results in gas formation. Let's say gas evolution reaction. Heat absorption or emission and light emission are also signs that a chemical reaction is taking place, because those are all, emitting light or emitting heat, it's not creating energy, but that energy has to come from somewhere. Absorption also usually indicates, so if something feels cold or feels like it's getting colder, that heat's going somewhere. Now, sometimes it's just ice.
May I have your attention, please? This is Aqueous IED.
So burning is always a chemical reaction. A chemical cold pack becomes cold, but only when you break the barrier inside that separates two substances. And as they react, they absorb heat. And then glow sticks emit light because the two substances mix and they react. So those ones don't really have specific names like the other ones that we've looked at, but they're also chemical reactions. You can be fooled, though, just by looking at something. For example, when water boils, those bubbles are not the result of a chemical reaction. We've talked about this. Boiling is a physical process. Also freezing, right? You could freeze water, form a solid from a liquid, but it's a physical process. And then you can also have chemical reactions that occur without any obvious sign. So they can be invisible. Pretty much all the reactions we're going to do in this class are going to have some sort of obvious sign. All right, so which changes involve a chemical reaction? So butane burning in a lighter, is it a chemical reaction? It's the easy one. It's burning. Actually, I'm going to write reaction. The other ways that we know, though, is that it's producing heat and light. as butane evaporating out of a butane lighter. I see one no. Is that a chemical reaction? Evaporating? It is not. So it's like if you left water out, or if you leave a glass of water out, or if you spill water on the ground, it eventually dries up and evaporates. But that's just a physical process. It's like boiling at low temperature. So no reaction. Wood burning. Similar to butane burning. Again, producing heat and light. This last one's kind of tricky. Dry ice subliming. We have talked about this one before. Is that a chemical reaction? I was thinking of it from the perspective of when we have solid dry ice, which is solid CO2, and it becomes a gas, is it still CO2? Yeah. Yeah, so it's still CO2, so there's not a chemical reaction. Same thing with butane evaporating or water boiling. The molecules are staying the same, just a different form. So there's no reaction for that one either. This microphone's hot. All right. So we represent this. I've mentioned it a few times, right? We're rearranging atoms to form new molecules. Sometimes more complicated, sometimes simpler molecules. The way that we keep track of that is through chemical equations. So they represent what's happening on an atomic scale, how the atoms are rearranging. How many of them also, and in what proportions. Because remember, when we have any reaction, we're not creating matter, we're not destroying matter. So all of the atoms that we start with have to be there at the end of the reaction also. So our substances on the left side of our reaction arrow, this one in the middle, are our reactants. They are the things that are reacting. So these are our reactants. The substances to the right of the arrow are the products. So read this. We read this like we read anything, right? Left to right. So we have our reactants, they react, form products.
May I have your attention, please? Aqueous IED.
So we also note the physical state of each reactant or product in parentheses after the formula. Sometimes it'll be, won't be subscripted, right? So it'll be the same size as the rest of the formula. Other times it will be a subscript. I'll usually write it as a subscript. So G here is gas. So all of our reactants and products are gases. You can also have L, which is liquid. The most common one probably is AQ, which means aqueous. You can also have S, which is solid. The key difference between aqueous and liquid is aqueous is when you have something dissolved in water. So pretty much all of the stuff we're going to be looking at is going to be aqueous. It's going to be something dissolved in water. Liquid would be something that is by itself a liquid. So like nail polish remover, acetone would be a liquid. And water is a liquid. Oh, of course, it's always on the next slide. So there is a table in your book, gas, liquid, solid, aqueous, which again is a water solution. So something dissolved in water. So as I was mentioning, we're never going to lose atoms as a part of a chemical reaction. We're never going to gain extra atoms as a part of a reaction. So in this one, we have 2 oxygen atoms on the left side. So if our reaction is down here, I'm going to leave it. And then we have 2 oxygen atoms and 1 oxygen atom on the right side. Right, so a total of 3 oxygen atoms. So this equation, this chemical reaction, needs to be balanced so that we have the same number on the left and the right. So similarly, on the left side we have, right, CH4 has 4 hydrogen atoms, but on the right we only have 2 hydrogens in H2O. So also unbalanced. So we're going to create a balanced chemical equation by adding coefficients to, or numbers in front of, each of our molecules or atoms, atoms or molecules, products or reactants, to multiply them. So we have the same number on both sides. So these are the coefficients that were added. 2 and a 2 there. So now when we look at this, we have 2 oxygen atoms here reacting with 1 methane to create 1 CO2, carbon dioxide, and 2 water molecules. So when we put this coefficient in front, it's saying that now instead of just having 1 water molecule, it's a 2, so we have 2 water molecules. And then if we go through, let me double check this isn't on, yeah, okay. So then we can go through and also just count the number of atoms on each side. So if on the left we have carbon, we have hydrogen, we have oxygen, just counting the total number of each. We have 1 carbon, we have 4 hydrogens, 4 hydrogens here, and then we have 2 times O2. So each of those has 2 oxygens. Multiply that by 2. We have 4 oxygens. Then on the right side, we'll do the same thing. Carbon, hydrogen, oxygen. Count these here. We have 1 carbon. We have 2, and then there are 2 hydrogens in each water molecule. So 2 times 2 is 4. And then we can also look at our number of oxygens. So there are 2 oxygens in CO2. And then this is 2 times the 1 oxygen in each water for a total of 4 oxygens.
May I have your attention, please? This is Aqueous IED.
So we have the same number of atoms now on each side. All we had to do was add a coefficient of 2 to 2 of these molecules. So to put this into sort of a formula that you can follow, write a skeletal equation by writing the correct chemical formulas for each of the reactants and products. So that's like we had before, where we've got just the methane, oxygen, carbon dioxide, and water. We'll, of course, talk about predicting those sorts of things. And then if an element occurs in only 1 compound on both sides, balance it first. So if it's in 1 compound on both sides, balance it first. And then if there is more than 1 such element, balance metals before nonmetals. Then if you have an element, if an element occurs as a free element on either side of the chemical equation, balance it last. So free elements on either side, balance it last. And you always balance free elements by adjusting the coefficient on the free element. It's adjusting the coefficient of the free element. Then if the balanced equation contains coefficient fractions, so let's say we need half of an oxygen, if we had half O2 and we needed 1/2, multiply the entire equation by the appropriate factor. So if you have 1/2, then you multiply the whole thing by 2. Not just oxygen, but everything else as well. Then the last step is to check to make certain the equation is balanced by summing the total number of each type of atom on both sides. And then this is key. Do change the coefficients. Do not change the subscripts. Because if you change the subscript, you change the molecule. It becomes something else. It's not very green. Okay, so we'll put this into practice now. And again, this is why you need to know charges and nomenclature and polyatomic ions, because you'll get problems like this, where it's just written out like this. So we have chromium oxide and solid carbon are reacting. All right, so reaction between. So these are going to be our reactants, just yellow, chromium oxide and solid carbon, so solid chromium oxide, to produce, let's do blue, solid chromium and carbon dioxide gas. What's the formula for chromium oxide? So we have Cr and O. What's the charge on chromium? It's in the name.
Are you looking at the oxygen? For chromium, isn't it like a transitional metal? Or
Yes.
Yeah, no?
It is a transitional metal.
Okay.
And the chromium 3, the 3 is telling us what the,
So it's a 3. Yeah.
it's a 3+ charge. Then oxygen always forms the same charge, which is a 2-. So going back to the nomenclature stuff, we always write the formula for an ionic compound so that the charges are balanced. Right, so if we have 3+ and 2-, we can use the crisscross. So we're taking just the magnitude of that, not the sign with it, of those exponents. This is going to be Cr2O3. Oh, and I'll write this too. So it's a solid. And that's reacting with solid carbon. So that's just carbon. And then I would leave room here for the, just in case we need to add coefficients. And then we're going to produce solid chromium. So if you're ever given a question like this and it says solid chromium, and it's just chromium by itself, or it's just carbon by itself, those are not going to have a charge. Yeah. What was that?
Is that an S or is that a 5?
Oh, it's an S. Yeah. Yeah, I'll try and make sure I'm very specific about that. But yeah, those are S's because each of those is a solid. And then we're also going to produce carbon dioxide gas. So this is a non-metal molecular compound. So carbon, we're going to have 1 carbon. And then dioxide means we're going to have O2. And that's a gas. All right, so we have now the skeletal structure for this chemical reaction. All the formulas written out correctly. If you don't get the formulas correct, then it will balance incorrectly. The nice thing about these, or at least the thing that I like about them, is that they will always balance if you have the formulas correct. So it's kind of like solving a puzzle. but these rules can help make this easier. Okay, so we got our skeletal equation, wrote the correct chemical formulas. Now we're going to look to see if an element occurs in only one compound on both sides. We're going to balance that first. And then if there's more than one such element, we'll balance metals before nonmetals. All right, so elements that only occur in one compound on either side. So carbon only occurs in carbon dioxide. Chromium, which is, they're also by themselves, right? So they're only occurring in one on both sides. We have chromium also occurring here. And chromium is a metal, carbon is not. So we'll balance chromium first. So how do I want to do this? We're going to balance chromium first. And then I think this rule 2, if an element occurs as a free element on either side of the chemical equation, balance it last. So it kind of contradicts with this here. Since both of them occur as free elements, we're going to start with chromium still. But this rule does apply, right? Always balance free elements by adjusting the coefficient on the free element.
What does it mean by free element?
Oh, good question. So chromium here is a free element. It's chromium by itself. Carbon is also a free element here. It's just carbon by itself. The reason that you want to do that is because if we change the coefficient on chromium or carbon here, when they're by themselves, we don't change the number of anything else. So we'll start with chromium. We have 2 chromiums on the left. We have 1 on the right. So let's add a 2. Let me do it like this. I'm just going to put, all right, so we balance this one first. So now chromium's balanced. Now we can look at carbon, because carbon is our next element that only occurs once on either side, or in one element on either side. And we actually have, we look here, 1 carbon, so I don't need to do anything with that. We can move on to the oxygen. So we have 3 oxygens and 2 oxygens. The easy way to do this is if you have 3 on one side, 2 on the other, you swap those as the coefficient. So since this is 3 and 2's over here, I'm going to put a 2 here. I'm going to put a 3 here. Because now both of those are 6. I guess we probably should have started there. Because now we've added this 2. So that's changed the number of oxygens, but it's also changed the number of chromiums. So now we have, whoops. So how many chromiums do we have on the left side? 4. So we can go back and change this coefficient to 4 so that it matches. Yeah, I guess I should have started with oxygen here. Okay, so now we say we balanced oxygen, we balanced chromium, we balanced carbon now. So if we have 3 carbons on the right side, just 1 carbon on the left side, let's make this coefficient 3. The way that I usually think about these is I pick something, I start by balancing that, and then I just keep moving around. So if we had started with, I'll say we started with oxygen here, and we had done this coefficient, then that would have changed the coefficient over here, so that would have changed carbon. And so, well, it just changed carbon, so now we'll balance carbon, and then carbon would be by itself, and then you go back and look for anything that's not balanced. So our final step here will be to write out the number of each, even though going through, kind of check it as we go, just to make sure we didn't leave anything unbalanced. So chromiums, 2 times 2, 4 chromiums. For oxygen, it's 2 times 3, so it's 6. And then for carbon, it's 3 times the 1 carbon, so 3. Then on the right side, we have 4 for chromium. That one's easy because it's by itself. Oxygens, we have 3 times the 2 oxygens in every carbon dioxide. So 6. And then 3 times the 1 carbon in carbon dioxide for 3. So 4, 6, and 3 on both sides. Any questions? Balancing? If you do end up getting stuck and you feel like you're in a loop, because this can happen sometimes, and your numbers just keep getting bigger and bigger and bigger, after like, if you go through it like twice and that happens, you should stop, erase everything, and start over. Check your formulas first. Otherwise, just start with a different element. Because if you do have the correct formulas, it will always balance. All right. So now we're going to write a balanced equation for the combustion reaction of gaseous, so meaning a gas, C4H10, gaseous oxygen to form gaseous carbon dioxide, gaseous water. So it's C4H10, and that's a gas reacting with oxygen. Now, in other places, we haven't had to do this yet. And we did talk about this kind of way back. Oxygen is one of the Brinkelhoff diatomics, BRINCLHOF. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, which all exist as 2. Right, so it's O2. And these react to form gaseous carbon dioxide, so CO2 plus H2O, also a gas. So what should we start balancing first? So we balance free elements last, actually. Because if we balance everything else first, when we get to oxygen, all we have to do is change the number of these oxygens. So that makes it really easy. So we want to look for something that's only in one element on, or one compound on either side. So let's start here with carbon or hydrogen. So let's start with carbon because it's first. So if we have here 4 carbons, and then you do have to check, sometimes you'll have carbon in more than one compound. But it's just here, and then carbon is here. So we'll say we have 4 carbons on the left. We need 4 carbons on the right. Let's add a 4 coefficient there. Also, if you're not already, definitely do these in pencil. Because you can end up going through them multiple times, having to erase coefficients and replace them. So now we changed carbon, which changed our number of oxygens, but we want to balance oxygen last. So actually we're going to go back and we're going to balance hydrogen now. So on the left we have 10 hydrogens, and on the right we only have 2. So we want to multiply that 2 by something to get 10. Yep, so in this case 5. And now we'll balance our oxygens. Because we balanced everything else over here. Oxygen's the only thing left. So this is 4 times 2 for 8 oxygens. And then 5 times the 1, so we have 5 oxygens. So a total of 13 oxygens. So to get 13, we have O2 on this side. We can't change that 2, so we have to multiply it by a coefficient. One of the things you could do is just take 13 and divide it by 2. So that gives us 6.5, or 6.5. So just like with doing empirical formulas, sometimes you get these fractions. That table can also be helpful here. So because we have 0.5 or 1/2, we have to multiply everything by 2. I want to keep, whoops. I want to keep both of these on here. So I'm going to rewrite this, but everything multiplied by 2. So we're going to get 2 C4H10 plus 13 O2, and then 8 CO2, whoops, plus 10 H2O. So each of the coefficients gets multiplied by 2. Yeah.
So like, for the first part of the reaction where it says C4 and then 8 hydrogen 10, right, and then gas. So we didn't have any, so that's why you just put 2, right? Because we
Yeah,
multiplied
so-
by 2. Well, in theory it's like 1, right?
Right. This is another invisible 1, an implied 1.
Okay.
Okay, we don't need to write 1 because we wrote the molecule there.
Okay, thank you.
Mm-hmm.
What's a fraction? How do you know what's divided by? I mean, multiplied by.
What to multiply it by? The way you can just brute force it is just try a bunch of numbers. In this case, it's a really good question. Because at this point I've done it so many times, I just know them. If you can express it in terms of a fraction, like I did here, because the other way you could think about this is we have 13 oxygens and we have our O2, then it's, where can I write this? 13 over 2. So if you multiply that by 2, just like when we cancel out units to do unit conversions, multiplying that by 2 gives us 13. So this times 2 equals 13. So if we had another fraction, for whatever reason, if you got 13 over 4, then you would multiply by 4. And in that case, you would end up with some 0.25. I would refer to that table, though, from the last chapter in terms of which decimals, if you want that. Yeah.
So how come, so when we times the whole thing by 2, or multiply the whole thing by 2, how come the 4 next to the C and the 10, how come those numbers don't change?
Yeah, good question. So those don't change because that's sort of the definition of the molecule. It would be kind of like adding extra letters to a word. It changes the word. Yeah. So that C4H10 is that specific molecule. If you had more carbons in that, then it would be a different molecule. So what we're saying here is that we have 2 of this molecule instead of 1 of that molecule. Because we can't have half of an O2 molecule. Because then it would be just a single oxygen and be something different. Yeah. Mm-hmm. Any other questions? All right. So now we'll write a balanced equation for the reaction of aqueous lead acetate, lead 2 acetate, with aqueous potassium iodide to form solid lead 2 iodide, and aqueous potassium acetate. So again, this is one of the polyatomic ions. Review your nomenclature. So we're going to have lead, right, Pb, with what charge?
3 or 2?
2. Yeah, 2 plus. Acetate is C2H3O2?
Yeah, with the minus charge,
Yeah. Oh, it must be. Sorry. Yes. Okay, that's acetate. Yeah, the minus charge. Yep. So we're gonna have that aqueous lead acetate reacting with potassium iodide. So K, potassium is a plus charge. Iodine, the minus charge. And we're going to form solid. Move these over a little bit. Lead, again lead 2, and then iodide again, and potassium acetate. So all of these are ionic compounds. So for lead acetate, it's going to be Pb, and then because lead has a 2+ charge, we're going to need 2 acetates. So C2H3O2, all in parentheses, and that's aqueous, plus potassium iodide. That one's nice, because we have a 1+ charge and a 1- charge. So they're 1 to 1. And then those are going to form lead iodide. So lead has a 2+ charge, iodine's 1-. So we need 2 iodines to balance the charge of lead. And then this is just going to be potassium acetate. For the 2 there. Yeah.
So first, like the first equation you have on the top, right? You're balancing them out, and then that's when you're ready to find the coefficients for them.
Yes.
Okay.
Yeah. So I think especially on a problem like this where it gives you them all as their names, it can be very helpful to write out all the formulas first.
Balance them out, which is
Yep. Doing the crisscross or just looking at the charges, however you like to do it. So that's the step. At this step, right, so after this, going from here to this one, we're not going to change coefficient, or not coefficient, we're not going to change subscripts anymore. We're set in stone here unless we made a mistake. So, on this one, right, our first rule was to look for something that's only in one compound on either side. And these are all only in one compound on either side. All right, so this is the only lead on the left side, only lead on the right side, only acetate on the left, 1 acetate on the right, or it's the only one over here. Same with iodine. So when you've got this, you can kind of start anywhere. Because we don't have any free elements and we don't have anything that's in more than one compound. So we can just start with lead, which makes things pretty easy because lead, there's 1 on the left, 1 lead on the right, so that's balanced. This is where I say that I go from one compound to another. So if we went from lead here to lead here, then let's just do iodine next. So if we have 2 iodines here, there's only 1 iodine on the left side. Yep, so we'll use a 2 coefficient. So that changed our number of iodines. It also changed our number of potassiums. So then we can go say, okay, we have now 2 potassiums. On the right side, we have 1. So put a 2 there. So then we have the right number of potassiums. And then we also change the number of acetates. So now 2 acetates, and oh, isn't that nice? We have 2 acetates already on the left side. So just by doing that, we've balanced all of it. Right? Because if we go back to lead, because if we did acetate here, we go back to acetate here, there's 1 lead and 1 lead. So don't need to change anything else. But we can always check, whoops. So PB, it doesn't matter which order you write these in. I just go left to right. So 1 lead, 2 acetate, 2 potassium, 2 iodine. Well, So when I do, because I always do the reactants first for whatever reason, probably because it's on the left. Then when I go to the right side, I'll write out those elements in the same order that I did on the left side. Makes it easier to compare head to head. Whoops. So again, 1 lead, 2 acetates, 2 potassium, and 2 iodine. I don't know if I mentioned it in this class, but a really great way to study is to download these blank slides and try these again without looking at any notes. And if you can't figure it out, then look at your notes. If you still can't figure it out after looking at your notes, then you can come back and watch the video to see how I did it. Because if you can do it without looking at your notes, then you definitely know it. If you can't, then you don't know it. And sometimes you can get part of the way, but you need the notes to help get you there. Okay. Oh, were there any questions on this? Balancing? No? Okay. Yeah, from here on out, pretty much everything is going to be, well, we'll change gears a little bit, but this idea of balancing chemical reactions and the idea of using molar mass to convert between grams and moles, those are going to be the bread and butter of the rest of this class. Well, look at this. It's already all written out. So we want to balance this chemical equation. So where should we start? With what? Oh, for the previous one? Yeah. Correct. Yeah, you don't have to write the 1. Like that. Yeah. Those are implied. Yeah, we can start with the hydrogens. Because this is another one where we have oxygen and chlorine as independent or free elements. Always think Game of Thrones when I hear that. Like the free folk. That's not Game of Thrones. That's something else. No, it is. Yeah, people north of the wall, the free folk. Sorry. So the free elements we want to balance last. So we'll save those. Hydrogen then is the only thing that's not a free element. So what should I balance here?
So hydrogen already has 2, right?
Has 2 on the right. Yeah.
Right, and then on the left is none, so.
Yep.
Instead of
2 there.
Yep.
Okay.
So
Which, go ahead.
that changes our, is it CI, which is chloride now?
It is chloride. Yeah, it's hydrochloric.
Cl,
Yeah.
So.
Cl chlorine chloride. Yep. So that one's already good. Oh, didn't mean to do that. Because we have 2 now, and this is 2. So yeah, we have 2 oxygens on the left, 2 oxygens on the right. So we need to balance this. But then that changes our hydrogens. So then we'll go back, and now we have 4 hydrogens. So that changes our chlorine again. As balanced. So again, quickly go through hydrogen, chlorine, oxygen. And this is 4, 4, and 2. We'll do hydrogen, chlorine, oxygen in the same order. Hydrogens we have. Again, it's always the coefficient multiplied by the subscript. So 2 times 2 for hydrogen is 4. Then same sort of thing for chlorine. 2 times the subscript is 4. And then 2 oxygens. Yeah.
So in this
Mhm.
So would the free element be oxygen in this case?
Oxygen and chlorine are both free elements. It just happened to be that we had to go through it again because balancing oxygen here changed hydrogen, which changed chlorine again.
And like what defines like a free element? Is that like
It is when it's the element by itself. So oxygen and chlorine are both in that Brinkelhoff list, so they're diatomics. So this is their free element form.
got it?
So not part of a compound with other elements. Yeah. Any other questions? Okay. So yeah, I did mention this briefly. An aqueous solution is a homogeneous mixture. All right, so it's got the same consistency throughout. Homogeneous mixture of a substance with water. Most of the things we're going to do are going to be aqueous. Ionic compounds, when ionic compounds dissolve in water, they usually dissociate into their component ions. So you have something like sodium chloride will actually split apart into sodium, or split apart or dissociate, plus chlorine. So you can form an aqueous solution of sodium chloride by stirring table salt in a glass of water. Seems to disappear, but you can taste it still. This is actually the lab that we did where it was like, is dissolving something a chemical or a physical process? It's technically a chemical process because you're taking the sodium. If it's a salt, it's a chemical process. If it was sugar, I don't remember what the formula for sugar is. But sugar is a molecular compound. When you add it to water, it doesn't break apart. It remains sugar molecules. That's a physical process. So when ionic compounds dissolve, it's chemical. When molecular compounds dissolve, it's physical. So if we have this sodium chloride, there are no actual sodium chloride units in the water. So we've got chlorines and sodiums floating around because they're actually completely surrounded by water molecules. So substances that completely dissociate into ions are called strong electrolytes. They're called electrolytes because they can carry a current. So you can actually pass electricity through water with salt in it, and usually it's a light bulb you use to light up. All right, so pure water does not conduct electricity. There aren't any ions to shuttle those electrons across. But the ions from sodium chloride dissolved in water, in this case, if you have a battery, will cause this light bulb to light up. So I mentioned a couple times you can take a 9-volt battery and put it into salt water, and it will start to split water molecules apart. It's really cool. You can do that with distilled water, and it will not split the water molecules apart because there's nothing to conduct the electricity from one terminal to the other. Yeah.
So like, would that work if you're touching the light bulb, or does it have to have like a plastic like holder?
What do you mean touching the light bulb?
So like, you see how like there's like a plastic stand on the light bulb?
Oh, yeah, like this part?
Yeah, like do you have to, in order for that to work?
You don't have to be touching that. Because the electricity is only passing through, even if you were touching the like glass part of the light bulb, the electricity is passing through just the wires. So it'll be traveling up through here, and then up over to here, and then down the other side. Yeah. So strong electrolyte solutions conduct electricity, as well as dissociate completely into ions. Silver nitrate solution is also an ionic compound. Does not contain any AgNO3 units. There aren't any silvers and nitrates actually stuck together in the solution. So silver nitrate is also a strong electrolyte solution. And this is part of why we talk about these polyatomic ions as individual units, because when you add them to the water, the NO3 stays together. It just splits away from the silver. So the polyatomic ions dissolve, they dissolve as intact units. But not all ionic compounds dissolve in water. This really has to do with how strongly the water can pull the ions apart. If the ions are stronger at holding each other together than the water is at pulling them apart, they don't dissolve. So silver chloride is not soluble in water. So if you add it to water, it will stay as, and you'll see it as a solid block or chunk or, a solid at the bottom. So this leads us into solubility rules. So a compound is soluble in a particular liquid if it dissolves. And you'll know it dissolves because you'll add it to the solution or add it to the water and it will look like it disappears. That a compound is insoluble if it does not dissolve in the liquid. For ionic compounds, we have empirical rules of solubility, which is a table that you just have to memorize. And actually, I'm not going to make you memorize it. You just have to remember how to use it, because I don't like solubility rules. So they're determined empirically. If you can remember back to the lab where we're mixing the different liquids, that's the kind of empirical determination. It's like somebody went and they put sodium chloride in water and they said, that's soluble. Then they took silver chloride and added it to water and said, that's not soluble. So this is another table to have on hand at least. It can be a little bit intimidating at first. So everything on top, these are, so compounds containing the following ions are mostly soluble. So, put a line here actually. So these guys are soluble, except when they're combined with the exceptions. So if you have chlorine, bromine, or iodine, if those are paired with silver, mercury, or lead, the compound is insoluble, does not dissolve. Our bottom list is the opposite, where these ions, compounds containing the following ions, are mostly insoluble, except when they're combined with the exceptions. So if you had a compound that had hydroxide, if it's combined with anything other than these ones, then it's insoluble. If you have hydroxide, lithium hydroxide, sodium, potassium, or ammonium hydroxide, those are all soluble. So I think this table does just involve some getting used to it. But I'm sure we'll use it here, right? So copper sulfide. We have copper, we have sulfur. So we go back to our solubility table. We have copper and sulfur. So we first look for copper on the list, on the left side. And we don't have copper anywhere on the left side. We do have sulfur, or sulfide. Sulfide's here. So these are insoluble compounds, so copper sulfide should be insoluble unless copper is on the right side. So it's not lithium, potassium, sodium, right? So it's not over there. So copper sulfide is insoluble. Okay, so the next one, iron sulfate. Go back to our list. So we're looking for iron and looking for sulfate. If you don't find one, then look for the other. Sulfate, oh, you mean, so yeah, sulfate is here. And then these are, actually, let me try and do this too. Because it's kind of like this. Actually, I can make these actually straight lines. Yeah. So it's like this list. These are exceptions for chlorine, bromine, and iodine. If that makes sense. So these are the exceptions for sulfate. So sulfate compounds are mostly soluble, insoluble. Soluble? Soluble. They're mostly soluble. And then we have iron sulfate. So the only time that sulfate compounds are not soluble is when they're paired with strontium, barium, lead, or calcium. So iron sulfate is soluble or insoluble? Soluble. Good. You have lead carbonate. So carbonate is here. So it should be insoluble unless we find lead on the right side, but it's not in the exceptions. So it's insoluble. Ammonium chloride. So we go back over here. It is soluble. One of the reasons we know that is because ammonium is up here, and ammonium doesn't have any exceptions. It's always soluble. One of the things that I don't like about solubility rules is that there's not you don't have at this point a why. And we don't ever actually cover why some of these are soluble and some of them are insoluble. Any farther than the bonds between them are stronger than the bonds between it and water. Everything else we've talked about pretty much has some sort of reasoning behind that you have access to that I've taught you for how to work it out. Are there any questions about solubility there? Okay. So the solubility rules are important because it's how you determine if you have a precipitation reaction just based on the chemical reaction. So, for example, we talked about how laundry detergents have sodium carbonate to create these insoluble compounds to remove the ions magnesium and calcium from the solution. So these reactions are examples of precipitation reactions. We're forming solids. We're forming a precipitate upon mixing two aqueous solutions. So we have potassium iodide, solution mixed with lead nitrate. You get a brilliant yellow precipitate of lead iodide. Part of the way you know that too, just by looking at the chemical equation here, is that we have aqueous, or I should say aqueous and aqueous, forms a solid and another aqueous compound. So you don't always get precipitation reactions when mixing aqueous solutions. sometimes you get no reaction. So if you mix potassium iodide and sodium chloride, nothing will happen. You won't get a precipitate, you won't even get it generating heat. There's just no reaction there. And so that is one of the possibilities. So the standard question to ask on an exam would be, give you a reaction and say, or give you two reactants and say, does this produce a reaction? Then you got to go look at solubility rules, see if any of those things form solids, and then either write reaction or no reaction. So the key here is understanding that only insoluble compounds form precipitates. So if you use the solubility chart and one of the products is insoluble, you have a precipitation reaction. And the two solutions have to be soluble as well. So let's say we have potassium iodide and lead nitrate, mix them together. All right, so we got these two solutions with these ions floating around. Immediately after mixing, what are our possible combinations of ions? I don't think I've said this explicitly yet, but you're always going to have the positive ions are going to find a negative ion if they're going to react. You won't get potassium and lead. All right, those are two positive ions. Like charges repel, opposite charges attract. So our possible ions here, you can just start by writing out potassium. We started with potassium ion, but that's one of our possible combinations. Our other possible combination for potassium would be nitrate. And then we can write out our lead. So one possible combination would be lead iodide, would be PbI2, or lead nitrate. Now we know from our initial reactants that lead nitrate is aqueous. And we know that potassium iodide is aqueous. Actually, I'm going to go back. We're going to want to come back to that. All right, so now we go look at our solubility rules, and we're looking for potassium nitrate and lead iodide. So starting with potassium nitrate, potassium and nitrate are always soluble. So if any compound with nitrate, it will be soluble, no exceptions. Same with potassium. Lead iodide, though, we have iodine here. So most of those compounds are soluble, but lead, specifically lead 2+, is one of the exceptions. So lead iodide will be insoluble. So we said potassium nitrate is aqueous also. This is a solid. So do we have a reaction or no reaction? Yeah, we have a reaction because we're forming a solid. Yeah, so this would be a reaction, which I think will be on the next slide, probably. Yeah.
May I have your attention, please? This is Atlas IED.
So our lead iodide precipitates, and we'll get a big chunk of that at the bottom, but our potassium and nitrate ions remain in solution because they are still aqueous. All right, last thing we'll do here, just talk through these. To write equations for precipitation reactions, write the formulas of your two compounds being mixed. Those are your reactants. Below the equation, write the formulas of the ions, being sure to include those charges, because you'll need those to balance them. Then exchange the anions and write the ion formulas below the product side of the equation. Then you use solubility rules to determine if the new pairs of ions are insoluble. And if both of your new pairs that you form are soluble, then it's no reaction. If one or both is insoluble, then you can write your new formulas, balancing those charges. Then you can balance the entire reaction by adding coefficients. Yeah, let's just very quickly. Potassium hydroxide says KOH. And nickel 2 bromide. So those are our two reactants. And those are aqueous. So now we'll rewrite those formulas, but we'll write them as the individual ions. So K plus, OH minus, nickel 2 plus, Br minus. And then we stop the anions. So the anions are the ones with negative charges.
May I have your attention, please? This is Atlas IED.
So notice I just took the cations and I just shifted them over. Kept them in the same order. So potassium had hydroxide before. So now nickel gets hydroxide. And then potassium now will get bromide. Or bromide. Br minus. So now we can look at these pairs and see potassium bromide. We actually saw potassium always soluble. Nickel hydroxide, however, find hydroxide. So hydroxide compounds are mostly insoluble. And then nickel is not on the list of exceptions. So nickel hydroxide will be insoluble. Oops. Forgot to put that in. So this will be insoluble. This one's soluble. And because we had at least one form of precipitate, we have a reaction. And then we can write these with the charges balanced. This will be our solid. This will be aqueous. And then we can balance it. So we'll get can really start anywhere. So let's just start with potassium, because again, there's no free elements here. And each of these is only part of one of the compounds on either side. So to start with potassium, we'll say, okay, we got one potassium and we got one potassium. Those are balanced. We have one bromine on the right, but we have two bromines on the left. So out of two. Now, we could go either way, right? Because now that we changed that, we can go back and say, oh, well, potassium changed now. So let's go back and do potassium. We'll put a 2 here. And then hydroxide now has 2. On the right, we have 2 hydroxides. We have 1 nickel. And then on the left, we have 1 nickel. So they are all balanced. And then I guess just to be safe, we'll go through and do this. So 2, 2, 1, and 2. K, OH, and I, Br. We have 2, and 2, and 1.